Hi folks, in this video we're going to have a look at a capacitor question that is put into the context of defibrillators. So defibrillators use capacitors designed for use in portable devices. A particular capacitor found in many defibrillators has a capacitance of 50 microfarads. Part A of this question is asking what charging potential difference would be required to store 100 joules in a 50 microfarad capacitor. So we know that in order to work out the energy stored in a capacitor, there's a couple of different equations we could use. So the energy stored, or the work done in charging a capacitor, is equal to a half multiplied by Q times V, so that's the charge times the voltage. Or we could say that it's equal to a half times the charge squared over the voltage. Or we could say that it's a half squared multiplied by the capacitance times the voltage squared. So in this case, based on the information that we're given, we're going to use this last version of the equation. So putting the values into the equation, we know that the amount of energy stored is 100 joules, so we're going to have 100 is equal to a half multiplied by the capacitance, which is 50 microfarads. So that's 50 by 10 to the minus 6. And then that's multiplied by V squared. So V is what we're trying to find here. So if we rearrange that, we can bring the half over to the other side, where we will end up with 2 multiplied by 100. And I'm also going to move the 50 microfarads, which will become a divide when we bring it over to the left-hand side. And we also then want to square root that value in order to get an answer for V. So when we put that into a calculator, we get an answer then of 2000 volts. So very high voltage here to charge this capacitor. Okay, part B of this question says that doctors need to be able to recharge the capacitor in the defibrillator in a time of 3 seconds. So what average charging current is needed? So we know that there will be a movement of charge as the capacitor is charging, and we also know that that charge will flow very quickly at the beginning, but that it slows down over time as the capacitor becomes more charged. And that's because as it's building up on the plate, it gets harder and harder to move those electrons onto that negative plate. So if we want to find the average current, what we're going to need to do is we can use the equation that current is equal to charge divided by time. Because that's what current is, it's the rate of flow of charge. So if we find the average current, we can do that by taking the total amount of charge and divide it by the total time taken. So we need to figure out how much charge is stored on that capacitor. And to do that, we can use our definition for the capacitor, which is the charge stored per unit voltage or per unit potential difference. And if I rearrange that, the charge is equal to capacitance times voltage. So our capacitor is 50 microfarads and our voltage is 2000. And when we do that, we get 0.1 coulombs of charge. So that's the total amount of charge on the capacitor. So if we want to figure out now the average charging current when it takes 3 seconds for it to charge, we can use I is equal to Q over T. The charge is 0.1 divided by 3 seconds. And that gives us 0.033 amps. Finally then, part C, we're asked to calculate the mean charging power, so the average power. Well, for this, we know that power is the amount of energy that's transferred per second. So it's the energy transferred per unit time, per second. Well, we already know from the question that the capacitor has 100 joules of energy. And we also know that it charged in 3 seconds. So 100 divided by 3 gives us an answer of 33.3 watts. So that's 33.3 joules of energy transferred each second.